Good morning, everybody. Today, our topic for discussion is quantum mechanics. The outline of our topic is Introduction to Quantum Mechanics, Black Body Radiation and Planck's Law, Photoelectric Effect, Compton Effect, de Broglie's Hypothesis, Wave Particle Duality, Division-Zermer Experiment, Heisenberg's Uncertainty Principle, Born's interpretation of the wave function, Schrodinger's time-independent wave equation, particle in one-dimensional box. Now, coming to the introduction part of quantum mechanics is a new branch of study in physics which is indispensable, that means very understanding to understand the mechanics of particles in the atomic and subatomic scale. The motion of macroparticles can be observed either directly or through microscope. Classical mechanics can be applied to explain their motion, but classical mechanics fail to explain the motion of microparticles like electrons, protons, all this subatomic level. Max Planck, he is the scientist who proposed this quantum theory to explain black body radiation, and Einstein is the one who developed it, who applied it to explain the photoelectric effect. Our first topic in quantum mechanics is black body radiation. What is a black body? Which emits all kind of radiations by giving heat treatment, and which absorbs all kinds of wavelength, different radiations when incident on it without reflecting. Okay, a body that completely absorbs all wavelengths of radiation incident on it at low temperatures or emits different wavelengths of radiation at higher temperatures is known as a black body. A graph has been, okay, now in the next slide I'm going to show you the graph of intensity versus wavelength. A perfect black body is, we don't have a perfect black body. Nearest approach is lamp black or platinum black. The temperature of the body is raised to different values and distribution curves are plotted for different temperatures. This is how the black body radiation, how it is varying. So at different temperatures, energy distribution is like that. If you observe clearly here, the energy of that, it is increasing with the increasing of temperature, and uh, the energy is increasing up to some wavelength, lambda max. And after that, it reaches a maximum value, energy uh, emissive power, it reaches a maximum value. After that, again, it decreases with further increase in wavelength. So in order to explain this black body radiation, Stefan Boltzmann, he one of the scientists who tried to give proper relation between the energy emitted and temperature. The emitted energy is proportional to fourth power of temperature, and here proportionality constant is sigma equals to sigma t power 4. Okay, here T is the absolute temperature, and this is Wien's displacement law. Another one is there here. Energy emission is maximum at one particular lambda for any particular temperature. We call that the lambda as lambda peak for that particular temperature, and lambda peak value into temperature equals to, it is a constant. This explanation is given by Wien, and we call it as Wien's displacement law. And Wien's another law, E and maximum emissive power is directly proportional to T power 5 or constant into T power 5. Wien's law is valid at lower wavelength region, whereas it deviates from experimental values at higher wavelength region. Next, Raleigh is another scientist who gave some empirical relation to give proper explaining the black body radiation. The relation is U lambda d lambda equals to 8 pi kb t power minus 4 d lambda. This equation is also correct for, following the, could able to explain the intensity fall in the intensity in the longer wavelength side. However, it fails to explain the lower wavelength side of the spectrum. So there is Wien's law is at a higher wavelength side, and whereas this is Rayleigh's law is the other side, it could able to explain the relation. Okay. For the radiation power and the fixed temperatures, two formulas were obtained using classical theories. Which one is correct? And all these relations are E lambda equals to C1 lambda power minus 4T, and E lambda equals to C2 lambda power minus 5 E power minus CQ C by lambda T. These two relations will help us the variation at lower wavelength side and higher wavelength side. Later, Planck, Max Planck is the scientist who proposed this Planck's radiation law, approached the quantum theory in order to give proper explanation for black body energy distribution. Planck assumed that the walls of the black body consist of a large number of electrical oscillators vibrating with their own natural oscillator possesses an energy equal to h nu, where h is the Planck's constant and mu is the frequency of the oscillator. An oscillator may lose or gain energy by emitting or absorbing photons respectively. Planck derived an equation for the energy per unit volume of black body in the entire spectrum of black body radiation and is given by E lambda d lambda equals to 8 by hc by lambda power 5 into 1 by e power h u by kBt minus 1 d lambda. This is the final equation for energy, emission of energy in Planck's radiation law by following the Planck's postulates. Okay, and photoelectric effect. This is one of the concept which was not given a clear-cut explanation by classical mechanics. What is a photoelectric effect? Photoelectric effect is nothing but when any light of proper wavelength is incident rate on any metal surface, photoconductive metal surface, the electrons on the surface of the metal will absorb the energy and they excite and they emit energy and they release from the surface will start traveling. Okay, it gains kinetic energy. Okay, inconsistency with the classical light theory. According to the classical wave theory, maximum kinetic energy of the photoelectron is only dependent on the incident intensity of the light and independent of the on the light frequency. However, experimental results show that the kinetic energy of photoelectron is dependent on light frequency. So when incident light energy with some proper frequency is incident on metal plate, what happens? The electrons on the metal surface will acquire energy by absorbing the photon energy and emit the electrons, and electron will gain kinetic energy. This is the photoelectric effect, and because of the moving of these electrons, that we call this the photoelectrons, and the contribution of these electrons towards the current, we call it as photoelectric current. And if you observe the graph, how it will be, plotted between temperature and frequency. This is how the variation here u naught. Once we extrapolate the frequency curve, u naught is, we call it as threshold frequency. That means this is the minimum frequency required for the radiation in order to excite the electrons, gain the electrons and release from the metal surface. Energy quanta. Photoelectric experiment results suggest that the energy in light wave is contained in discrete energy packets instead of continuous, which are called energy quanta or photons. The wave behaves like particle. The wave behaves like a particle. The particle is photon. Planck's constant equals to H value 6.625 into 10 power minus 34 joule second. Photon energy H nu. Work function of the metal material H nu naught. Maximum kinetic energy of a photoelectron Tmax equals to H into nu minus nu naught. Planck-Einstein energy quantization law and photoelectric effect. As we know, E equals to H nu and U equals to C by lambda. And we know E is equal to mc square. There, if I replace H nu by C square, our final equation with the application of these two equations, we can gain H nu equals to W plus half mv square. Here, W is nothing but work function and half mv square, it represents the kinetic energy of the photoconductive electrons. And H nu is the incident energy of the radiation. Our next topic is Compton effect. A phenomenon called Compton scattering provides additional direct confirmation of the quantum nature of the electromagnetic radiation. Here, X-rays impinges on matter. Some of the radiation is scattered just as the visible light falling on a rough surface undergoes diffuse reflection. Scattered radiation here, it is having two frequencies. One is smaller frequency and longer wavelength than the incident radiation. The other wavelength is not modified. The wavelength of the scattered radiation depends on the scattered angle phi. Based on the classical principles, the scattering mechanism is induced by motion of electrons in the matter caused by the incident radiation. This motion must have the same frequency as that of the incident wave because of forced vibration, and so the scattered wave radiated by the oscillating charges should have the same frequency. There is no way that the frequency can be shifted by this mechanism. Now, that is classical explanation. Now let us have a look of quantum explanation. The quantum theory, by contrast, provides a beautifully simple explanation. We imagine the scattering process as the collision of two particles, the incident photon and an electron at rest, as shown in this figure here. The photon gives up some of its energy and momentum to the electron, which is at rest, which recoils as a result of this impact, and the final photon has less energy, smaller frequency, and longer wavelength than the initial one. Theoretical derivation. Suppose that lambda naught and lambda are the wavelength of the incident and scattered radiation respectively. The Compton effect could be described by the following procedures using relativistic theory and energy conservation. Momentum conservation using cosine principle at the same time. In this Compton effect, we consider the collision as elastic collision because it is following energy and momentum conservation both. The key points of derivation procedure is relativistic theory E equal h nu, which is we represent as hc by lambda. Here E is equal mc square. By combining these two, E square equals to cp square plus m naught c square. When m naught is equal to 0, that means when the electron is having some when it is in motion, the momentum is equal to P equal to E by C, H nu by C, that is equal to H by lambda. Energy conservation before the collision and after the collision. Before the collision, for the energy for photon and electron equals to H nu naught plus M naught square equals to, after the collision, what is the energy equation? H nu plus mc square. H nu is for photon, mc square is for electron. The same thing I can represent as mu naught instead of C by lambda. Here I'm taking out the C both sides. H by lambda naught plus m naught C equals to H by lambda plus mc. For electron, this is for the energy conservation. For electron, we have E square equals Cp square plus m naught C square whole square. Both sides are square. Mv square equals to mc square minus m naught C square. The momentum conservation, now we are going H by lambda naught P equals to H by lambda into P plus mv square. Mv square equals to H by lambda naught square plus H by lambda. This is the equation we got. So the mv square can be deleted from second equation and third. Then we will be having this final equation in the form of equation 4. Squaring 1 and subtracting equation 4. We will be having the last 0 equals to 2m naught C equal into H by lambda naught minus H by lambda minus 2 H square lambda naught lambda cos phi. The above equation can be rewritten as this is all mathematical simplification. Lambda minus lambda naught equals to H by m naught C into 1 minus cos phi. Here 1 minus cos phi is nothing but 2 into sin square pi by 2. So applying that 2 into H by m naught C sin square pi by 2. Here 2 lambda C sin square pi by 2. Here lambda C is the Compton shift, which is equal to H by mc, that equals to 0.00243 nanometer. This is the schematic diagram how here photon is incidenting on an electron which is at rest. Now photon is moving with the same frequency with a lesser energy, and electron is recoiling by absorbing the energy from the photon. Now the other concept is de Broglie hypothesis. The de Broglie's hypothesis says matter is having the dual nature. The dual nature of light, possessing both wave and particle properties, was explained by combining Planck's expression for the energy of a photon equals to h nu with Einstein's mass energy relation E is equal to mc square, where c is the velocity of light, h is Planck's constant, m is the mass of the particle. That means we are combining the properties of photon and properties of a particle. H nu equals to mc square, introducing mu is equal to c by lambda, and finally we will get mc square is equal to hc by lambda. Lambda is equal to h by mc, that is equal to h by t, where t is the momentum of the particle, lambda is the de Broglie wavelength associated with a photon. De Broglie proposed the concept of matter waves, according to which a material particle of mass m moving with velocity v should be associated with the de Broglie wavelength lambda given by lambda equals to h by p, that is nothing but h by m. The above equation represents the de Broglie wave equation. Now, wave particle duality we are applying to the nature. So particle-like wave behavior, example, photoelectric effect, and wave-like particle behavior, example, Davidian-Germer experiment. Now, combining these two, we will get wave-particle duality. Mathematical description of the momentum of the photon, we can represent it as P is equal to h by lambda. In the same way, the wavelength of a particle is lambda equals to h by p. Here, lambda is called the de Broglie wavelength. Next, Davidian and Germer's experiment. This is the schematic diagram for the apparatus. So, if we directly observe the graphs by obtaining after finishing this experiment, the electron beam is accelerated by 54 volts is made to strike the nickel crystal, and a sharp margin is occurred at angle of 50 degrees with the incident beam. The incident beam and the refracted beam in this experiment make an angle of 65 degrees with the family of Bragg's planes. D equals to 0.091 nanometer per nickel crystal. According to Bragg's law for maxima in the refracted pattern, L lambda is equal to d sin theta, right? Here, first order plane we are taking, n equals to 1, lambda equals to 2d sin theta, and here theta value is 65 degrees for a 54 volt. I mean, the electrons will be recoiled with 54 volts. The de Broglie wavelength associated with the electron is given by, we know if the potential of the electron, if it is 54 volts, the formula, direct formula is 12.25 by root V by applying the 0.166 nanometers. And from Bragg's law, we have got the value for lambda is to 1.6.165 nanometers. Both the values from theoretical and experimental are in good agreement. This experiment provides a direct verification of de Broglie hypothesis of wave nature of moving particles. The duality of light, the concept that waves carrying energy may have a corpuscular aspect and that particles may have a wave aspect. Which of the two models is more appropriate will depend on the properties the model is seeking to explain. For example, waves of electromagnetic radiation need to be visualized as particles called photons to explain the photoelectric effect. Now, we may get confused the two properties of light and ask what the light actually is. So at one particular point, we consider if we are treating it as photons, then we will partially neglect the wave nature. And especially at one instant, if you are considering it as wave, then you need to stop the process of assuming it as a particle. Next, the uncertainty principle. The Heisenberg uncertainty principle. It is impossible to simultaneously describe the absolute accuracy of the position and momentum of a particle. Delta P into delta X is greater than or equal to some quotient eta. Okay, it is greater than or equal to h cut by 2 pi. It is impossible to simultaneously describe with absolute accuracy the energy of a particle and the instant of time. So there are like two conjugate sets like momentum and displacement vector and energy and time. At the same time, delta J into angular momentum into angle the delta theta. Okay, these conjugate sets are following with this uncertainty. That means we cannot accurately describe the error in calculating that parameter. The Heisenberg uncertainty principle applies to electrons and states that we cannot determine the exact position of an electron. Instead, we could determine the probability of finding of an electron at a particular position. Next, Born's interpretation of the wave function or physical significance of a wave function. When we are treating the electron as a wave, then we need to represent the wave with some wave function psi. So, Max Born in 1926 gave a satisfactory interpretation of the wave function psi associated with a moving particle, postulated that the square of the magnitude of the wave function psi square or psi into psi star, because psi is a complex quantity, psi square it represents the probability density and psi is the probability amplitude. Thus, the probability of the particle within an elementary volume d tau is psi square d tau. Since the particle is certainly somewhere, the integral at psi square d tau over all space must be unity. That means the probability of that is 1. equals to 1, psi square d tau equals to 1. A wave function that obeys the above equation is said to be normalized. Energy acceptable wave function must be normalizable besides being normalized. An acceptable wave function should fulfill the following requirements. What are the three? It must be finite everywhere, it must be single valued, it must be continuous and have a continuous first derivative everywhere. Schrodinger time independent wave equation. In one dimensional, the equation is minus h square by 2m d square psi x by dx square plus vx psi x is equal to e psi x. In three dimensional, the same thing we will represent it as minus h square 2m del square psi of r plus vr psi r equals to e psi. And the application of Schrodinger time independent equation is particle in one dimensional box. Here particle is nothing but it is the electron. Okay, one dimensional box is nothing but when the electron is in its unit cell, when it is rotating the crystal, we consider it as it is there in the unit cell. Okay, the limitations are here like how in the figure it's represented. V is equal to x is equal 0 and x is equal to L. At limits potential V is equal to 0 for 0 is less than x is less than L, and V is equal to infinity for 0 is greater than or equal to x is greater than or equal to L. That means within the box the potential is 0 and outside or at the borders it is infinity. The Schrodinger one-dimensional time-independent equation is del square psi plus 2m into e minus v h square psi equals to 0. For freely moving particle, v is equal to 0 within the limits from x is equal to 0 to x is equal to L. Okay. And del square psi plus 2me by h square psi equals to 0. Here I substituted the value of v is equal to 0 in equation 1. Taking 2me by h square is equal, consider it as k square some constant. Equation 1 becomes then dou square psi by dou x square plus k square psi is equal to 0. Now equation 1 is similar to equation of harmonic motion, and solution of above equation is written as psi equals to a sin kx plus b cos kx, where a, b and k are unknown quantities, and to calculate them it is necessary to construct boundary conditions. Hence, we know what are the boundary conditions. When x is equal to 0, psi is equal to 0. So applying this finally gives b equals to 0, which is an equation 6. And when at x is equal to L, psi is equal to 0, the other boundary condition, if I am applying this, a sin kl plus b cos kl is equal to 0. Anyway, b is equal to 0, we know. So a sin kl will be 0. So here a cannot be equals to 0. So obviously sin kl is equal to 0. Kl equals to for all n pi. Okay, all n pi values sin kl is equal to 0. So k equals to n pi by L. Substituting the value of k in equation 3, 2me by h square is equal to n square pi square by L square. E will be n square h square by 8ml square by substituting and simplifying. In general, En equals to, that is energy in nth level, equals to n square h square by 8ml square. The wave equation can, okay, now the final wave equation can be written as psi equals to a sine of n pi x by a. Let us find the value of a if an electron is definitely present inside the box. Then from normalization condition, integrating minus infinity to plus infinity to psi square dx equals to 1. So applying the here wave equation, a square sine square n pi x by L dx is equal to 0. Applying the limits 0 to L, we will get 1 by a square. Here a equals to under root 2 by L. Okay, from equations 10 and 11, the final wave equation I can write psi n equals to square root 2 by a sine of n pi x by L. Equation 9 represents an energy level for each value of n. The wave function is given in equation 12. Therefore, the particle in the box can have discrete values of energy. These values are quantized, not that the particle cannot have zero energy. The normalized wave function psi1, psi2, psi3 given by equation 12 is plotted. The values corresponding to each En value is known as eigenvalue, and the corresponding wave function is known as eigenfunction. This is the representation of wave function, and here how the energy values are varying. N level, E will be pi square h square by 2m a square. For n is equal to 1, n is equal to, n is equal to 3, n is equal to 4. This is the wave function, how it is varying. Particle in an infinite potential well, 4 low. First one, 4 lowest discrete energy level, B, corresponding wave function, C, corresponding probability functions. This is all about your introduction to quantum mechanics.